To virtualize the central processing unit, an operating system needs to share the physical processor among many jobs running seemingly at the same time. The basic concept is direct: run one process for a little while, then run another one, and continue this cycle to achieve time sharing. However, building this virtualization machinery presents two core architectural challenges: performance and control. We must implement virtualization without adding excessive overhead to the system, while simultaneously retaining absolute control over the central processing unit. Without control, a process could run forever, take over the machine, or access restricted information. Balancing these two requirements is a foundational challenge in system design. To maximize execution speed, operating system developers engineered a technique called limited direct execution. The direct execution phase of this strategy means running the program directly on the physical hardware central processing unit. When starting a program, the operating system creates a process entry in its internal process list, allocates memory, loads the program code from the disk, locates the entry point such as the main routine, and jumps directly to it. While running user code natively on the hardware ensures maximum performance, it creates a dangerous problem. Without enforcement boundaries, the operating system cannot stop a program from performing unauthorized actions or successfully force it to relinquish the processor. To solve the problem of restricted operations, modern hardware architectures introduce distinct execution environments, establishing user mode and kernel mode. Code executing in user mode is heavily restricted. For example, it cannot directly issue input-output requests to a disk or access raw system resources. Attempting a restricted operation in user mode causes the processor to raise a hardware exception, prompting the operating system to immediately terminate the offending process. Conversely, the operating system itself runs in privileged kernel mode. In kernel mode, code can execute any instruction and access all physical resources, allowing the operating system to safely coordinate hardware functions. When a user process needs to perform privileged action, like reading a file from a disk, it relies on a system call interface. To execute a system call, the application runs a special hardware trap instruction. This instruction simultaneously jumps into the kernel and elevates the processor privilege level to kernel mode. To prevent user programs from jumping arbitrarily into secure kernel code, the operating system configures a protected trap table at boot time. Running in privileged mode during the initial boot sequence, the kernel programs the hardware with the exact memory addresses of its exceptional event handlers and system call trap vectors, ensuring all entries into the kernel route through verified pathways. When a trap occurs, the underlying hardware must save the caller's execution state, including the program counter, flags, and general-purpose registers, onto a per-process kernel stack to ensure a flawless return. To execute the requested operation, the user code specifies a system call number inside a hardware register or stack location. The trap handler inspects this index, validates it, and executes the corresponding kernel routine. Once the work completes, the operating system invokes a specialized return from trap instruction. This instruction pops the saved registers off the kernel stack, lowers the execution privilege level back to user mode, and returns control to the instruction following the initial trap. Beyond restricting operations, the operating system must actively switch between processes to implement time sharing. This creates a logical paradox. If a user process is actively executing on the central processing unit, the operating system is not running, meaning it cannot take any automated action. Historically, early implementations used a cooperative scheduling approach, trusting applications to periodically give up control using an explicit yield system call, or by executing standard input-output operations. However, if a cooperative program hits an infinite loop or encounters a disruptive bug, it completely freezes the machine, leaving a total system reboot as the only viable mechanism to reclaim control. To enforce control without relying on application cooperation, modern systems use a hardware timer interrupt. A physical timer device is programmed at boot time to generate a hardware interrupt every few milliseconds. When this timer fires, the currently running process is instantly suspended, its registers are saved to its kernel stack, and control transitions directly to a pre-configured operating system interrupt handler. Once the operating system has regained control of the central processing unit, an internal component called the scheduler determines whether the current process continue executing or to initiate a context switch to transition to a different waiting program. If the scheduler decides to switch execution paths, the operating system executes a low-level context switch by running hand-coded assembly routines. This mechanism saves the remaining kernel registers and the stack pointer of the active process into its process structure entry, and restores the kernel registers and stack pointer of the upcoming process from its respective structure. By swapping the active stack pointer to the new process's kernel stack, the operating system transitions context mid-routine. When the kernel subsequently executes its final return from trap instruction, the hardware pops the execution state of the new process, completing a secure and highly efficient transition.